In the market square, every shopper found their umbrella. 5 colors, 5 gentle crowds. But we could see them, because we only watched 2 things, income and spending. What happens when there are 64 things to watch? Or 600? Come this way, down the pedal lane, through the paper doors, into the origami hall, a place where complicated shapes learn to lie flat. Today, we meet principal component analysis, PCA, a quiet art of keeping what matters and gently letting go of the rest. Here is a handwritten 3, just 8 little rows of 8 little squares. Watch what happens when we unfold it. 64 paper squares, 64 numbers. That's what the computer sees, not a 3, a strip. And we don't have 1 digit, we have 1,797. The hall fills up, strip after strip after strip. Can you still see the shapes? Neither can Kiko. This is the quiet trouble with many features. Too many folds, and the shape disappears. We need fewer numbers that still tell the same story. That is exactly what PCA does. Let's read this together, slowly. 1 handwritten digit is a small grid, 8 rows by 8 columns of pixels, and 8 times 8 gives us 64 numbers. Next line, we have 1,797 digits, and each one carries 64 features. So picture it, every single digit becomes a long strip of 64 values, and there are nearly 1,800 strips filling the hall, and the last line whispers the problem itself. Too many folds to see the shape. Hold that feeling, it is exactly why PCA exists. Let's bring the digits in, one gentle line at a time. Low digits, and the drawer opens. 1,797 handwritten digits drift onto the table. The shape tells us everything. 1,797 rows, 64 columns. Every row is 1 digit, every column, 1 pixel of ink. We fold them into a data frame, pixel 0, through pixel 63, and 1 golden column for the answer. And here they are as pictures. A 0, a 1, a 2, written by real human hands, long ago. A little wobbly, a little imperfect. That's all right. Wobbly is exactly what we're here to learn from. Let's walk through this code, line by line. First, the imports. Low digits from Sclearn datasets, then Pandas as PD, NumPy as NP, and Matplotlib's Pyplot as PLT. We call low digits and keep the result in a variable named digits. Printing digits.data.shape shows 1,797 rows and 64 columns. Digits.target.shape is simply the 1,797 labels, and the unique values run from 0 to 9. Next we build a data frame called df, 1 column per pixel, named pixel_0 through pixel_63, then add the digit column from digits.target. df.shape is now 1797 by 65. Finally, a small loop draws the first 10 digits in soft gray, each with its label written above it. Before PCA can listen, every pixel must speak at the same volume. Some pixels shout, big values, lots of ink. Some barely whisper. If we skip this step, the loud pixels drown out the quiet ones, and PCA hears only the shouting. So, standard scalar, fit, and transform. Now every column has a mean of 0, and a standard deviation of 1. 64 voices, 1 gentle, even choir. Take a breath here. The interesting part begins now. Only a few gentle lines here. First we separate the pieces. X holds every pixel column of df. After dropping the digit column, 1,797 rows, 64 features. Y holds just the digit labels. Then we create a standard scalar and name it scalar. One call to fit_transform on X does 2 things at once. It learns each pixel's mean and spread, then rescales every value, storing the result in X_scaled. The 2 print lines are our quiet check. The mean rounds to about 0, and the standard deviation to about 1. 64 columns, all speaking at the same soft volume now. Here is the whole idea of PCA, in a single beam of light. Kiko holds a folded crane up to the window. Look at its shadow. The crane has depth. The shadow is flat. And yet, you can still tell it's a crane. A shadow is a projection. 3 dimensions, pressed gently into 2. But notice, the angle matters. Turn the crane the wrong way, and the shadow becomes a blob. The story is lost. Turn it just right, and the shadow keeps almost everything. PCA searches for that angle. the direction of light that casts the most informative shadow of your data. That direction has a name, principal component 1. Then it finds the next best angle, at a perfect right angle to the first. Principal component 2, not chosen by us, found by the mathematics of the light. Read the screen with me, softly. A shadow is a projection, 3 dimensions pressed down into 2, and yet the crane is still a crane. That single line is the heart of PCA. Below it, 2 definitions. PC1 is the angle of light that casts the most informative shadow, the direction where the data spreads out the most, where the story stays clearest. And PC2 is the next best angle, turned exactly 90 degrees from the first, perpendicular, so it catches whatever the first shadow missed. 2 angles, 2 shadows, chosen not by us, but found by the data itself. Now, let's watch it learn, slowly, step by step. 1 strip, 64 squares, fold, 32. Each new square is a careful blend of 2 old ones, nothing thrown away carelessly, just combined. Fold again, and again, 8, and then 2. 64 numbers have become 2. PC1, 3.9, PC2, minus 1.2, one little card, that still remembers it was a 3. Now watch every strip in the hall do the same, and look at where the cards land. The zeros gather here, the 6s, over there, the 3s drift into their own soft pink neighborhood. No one told them where to sit. The shadow angles did that, but how much of the story did we keep? The jars will tell us. Jar 1, principal component 1, fills to 46%, nearly half the story, in a single number. Jar 2 adds 22, together, 68. Jar 3, 11 more, 79. Each new jar adds a little less, and the curve climbs gently, until it touches the golden thread, 95%. That's the quiet agreement we make. Keep enough jars to hold 95% of the story, and let the rest go. And why go to all this trouble? The hourglasses know. Training on all 64 features, 12 seconds. Training on the folded cards, 4. Same story, a third of the sand. If the folding felt mysterious, that's all right. We'll see it again now, in code. Let's trace the numbers on screen, one by one. A single-digit strip begins at 64 squares. Fold, 32. Fold, 8. Fold, just 2. The final card reads PC1 equals 3.9, and PC2 equals minus 1.2. Now the variance jars. PC1 holds 46% of the story. PC2 adds 22. PC3 11. PC4 6. Each jar a little less than the one before. Adding them together, the cumulative line climbs. 46, 68, 79, 85, on and on, until it touches 95%, the golden thread, and at the bottom, the 2 hourglasses. All 64 features take 12 seconds. 2 components, just 4. Everything we just watched is 3 lines of code, PCA, with 2 components, fit, and transform, and every strip in the hall folds at once. 1,797 digits, each now just 2 numbers. Explain at variance ratio. There are our jars, in print, and here is the curve we drew in light. It rises quickly at first, each early component carrying a great deal of story, then more and more gently. The dashed line is our golden thread, 95%, and the code tells us precisely where the clothespin goes. Notice something lovely, we never have to guess. The data tells us how many folds are enough. Let's walk this code slowly. First, we import PCA from sclern.decomposition. We create PCA with n components set to 2, then call fit_transform on x_scaled, saving the result as x_PCA. Printing its shape shows 1,797 rows and just 2 columns, and the first row is roughly 3.9 and minus 1.2, 1 digit, 2 numbers. PCA.explain at variance ratio tells us how much story each component keeps. Next, PCA_full fits all 64 components, just to measure, and np.comsum adds those ratios up into cumulative. We plot that curve across 64 ticks, draw a dashed line at 0.95, and finally np.argmax finds where the curve first crosses 95%, plus 1 gives us n_95. And now, the moment the whole hall was folded for, 1 scatter plot. Every marble is a handwritten digit, every color, a different number. Look at the zeros, a tight little island, keeping to themselves. The 6s, gathered like old friends. Some neighborhoods blur into each other, the ones and the sevens, leaning close. Of course they do. A hurried one can look like a 7, even to us. But pause on what just happened. This data lives in 64 dimensions. No one can picture 64 dimensions. And yet here it is, resting quietly on a table, seen at last. Only a handful of lines, and a whole world appears. First, plt.figure sets a generous canvas, 10 by 8. Then plt.scatter does the real work. The x positions come from column 0 of x_PCA, the y positions from column 1. The colors come from y, are digit labels, painted with the tab 10 color map. 10 soft colors for 10 digits, each dot small, size 15, and gently transparent at 0.8 plt.colorber unrolls the ribbon legend, ticked from 0 to 9. Then we name the axes, principal component 1, and principal component 2, give the chart its title, and plt.show lets all 1797 digits settle softly onto the page. Now we let a classifier learn from the folded cards. First, the honest split, 80% to learn from, 20% waiting behind the screen, unseen. Both hourglasses turn together. Station 1 learns from all 64 features. Station 2, from just 2. And Station 2 finishes, while Station 1 is still pouring. 4 seconds, against 12. But look at the dials. 97% accuracy with everything. 61 with only 2 components. 2 numbers are wonderful for seeing, but a little thin for deciding. So we ask for the golden thread amount instead. Components equals 0.95, and scikit-learn counts the jars for us. 29. 5 seconds of sand, and 96%. Almost all the wisdom, at less than half the folds, in less than half the time. That is the gentle bargain PCA offers. And notice one small kindness in the code. We fit PCA on the training data only, and merely transform the test data. The screen stays honest. Take a slow breath. This block builds 3 little stations. First, train_test_split divides x_scaled and y. 20% set aside for testing. Random_state 42. So the split is always the same. Station 1. We start a timer with time.time. Fit CLF_full. A logistic regression with max_iter 5000. On all 64 features. Then measure its accuracy with accuracy_score. Station 2. PCA 2, with components 2, fit_transforms the training data, and only transforms the test data, never refit on test. Another timer, another fit, CLF_2. Station 3, PCA 95 uses components 0.95, so scikit-learn chooses the count itself, about 29, and CLF_95 trains on those, 3 times, 3 accuracies, printed side by side. A new digit arrives, fresh from the letter slot. Watch it walk the whole path. First, the calibration frame, scaled, like every digit before it. Then the fold, 64 squares, down to 29. Then the loom, and the tag reads, 6. With 94% confidence, we turn over the true label, 6. Kiko approves. Remember this shape of things. Scale, fold, predict. Always the same steps, in the same order. For every digit that will ever arrive, 1 digit, 1 gentle journey. First, new_digit takes row 42 of x and reshapes it into a single row of 64 values, and true_label remembers its real answer from y. Then come the same 3 steps every digit must walk. Scalar.transform evens out its ink. PCA 95.transform folds it, 64 numbers down to about 29, stored in new_folded. CLF_95.predict reads the folded card and gives us prediction, while predict_proba offers a confidence for every possible digit. The prints tell the story. Prediction, 6. Confidence, about 0.94. True label, 6. Scale, fold, predict. Always in that order. Let's rest a moment, and weigh what happened. With everything, we were most accurate, and slowest. With 2 components, we could finally see, but the loom had too little to work with. With 29, the golden thread amount, we kept 96% of the accuracy, at less than half the time and size. PCA is not free. We always let a little go. The art is choosing. How much? Let's read the table on screen, row by row. First row, 64 features, 12.1 seconds, 97.2% accuracy, our most accurate, and our slowest. Second row, 2 components, just 4 seconds, but accuracy falls to 61%. Lovely to look at, thin to decide with. Third row, 29 components, 4.9 seconds, and 96.1%. That last row wears the golden thread, nearly all the accuracy of 64 features, at less than half the time. This is the quiet trade PCA offers, and the choosing is always ours. Time to put our work to rest. 3 gentle dumps. The scaler, wrapped first, because scaling always comes first, then the fold itself, the PCA, into its own paper box, then the loom, and the boxes nest, one inside the other, the way the steps nest in the pipeline. Whoever opens this parcel next month, or next year, will have exactly what we have now, the frame, the fold, the loom. Onto the shelf it goes, beside all its old friends. 3 saves, 3 loads. Let's walk them gently. First, we import joblib, then joblib.dump wrap scaler into a file called digits_scaler.pkl. The second dump saves PCA95 as digits_pca.pkl, and the third saves CLF_95 as digits_classifier.pkl. The frame, the fold, the loom, each in its own parcel. Below, the mirror image, joblib.load opens each file again. Scaler, PCA95, CLF_95 exactly as we left them, and the final comment whispers the path every new digit will walk. Scale, fold, predict. This quiet folding is everywhere. Face recognition began with it. Thousands of pixels folded into a few essential face patterns. Hospitals use it to carry the meaning of a scan, without carrying every pixel. In genomics, tens of thousands of genes fold into a handful of readable patterns. Weather stations, factories, satellites, wherever there are too many numbers to see, someone is holding the data up to the light, and keeping the best shadow. Read the list with me, one soft line at a time. Face recognition, thousands of pixels fold into just a few EGN faces. The essential face patterns. Medical imaging, whole scans compressed, while the diagnosis inside stays safe. Genomics, tens of thousands of genes, folded into a handful of readable patterns, and sensor networks, hundreds of chattering readings braided into a few clean signals. 4 different worlds, one same gentle gesture, hold the data up to the light, and keep only the best shadow. The hall grows quiet, the strips are folded away, the parcel rests on its shelf. Today you learned to see the unseeable. 64 dimensions, held up to the light, until they cast a shadow you could read. Through that far door, there's a courtyard, potter's wheels, apprentices, each one studying the mistakes of the one before, and fixing only those. They call it boosting, and it makes some of the finest models in all of machine learning. Rest here a moment. When you're ready, the next door is open. One last look at the screen. Episode 12, complete. The project handwritten digit recognition with PCA, 1,797 digits, 64 features, folded to 2 for seeing, 29 for deciding. The skills, read slowly, low digits and a pixel data frame, standard scaler, every feature at the same volume, PCA with components 2, fit transform and explain at variance ratio, the cumulative variance curve and the 95% golden thread, PCA with components 0.95, letting the data choose, logistic regression on reduced data, with the timing comparison, the 2-dimensional picture of high-dimensional data, and joblib, saving the whole pipeline. Next episode 13, gradient boosting, waiting in the potter's courtyard.